This is probably not the first or the last time that I talk about 15-minute cities. The concept of 15-minute cities says that an area or a neighborhood in a city qualifies as a good place to live in, so it has a high quality of life, if everything needed for the daily life, from shopping to healthcare to work or to education, is available within 15 minutes by foot or on bike. So in this tutorial, we are going to use the recently published City-to-Graph package to quantify accessibility on road networks in multiple global cities. So we will build a Python pipeline which will iterate over a number of cities, collects data on a number of relevant POIs, and then computes accessibility graphs for all these cities. And since this is a tutorial for this year's map challenge, we are going to cover one data source, which is everybody's favorite, OpenStreetMap. Let's see the Python part. Now we are going to learn about how to turn cities into graphs. If you have been following my channel, that you know that network science, since I did my PhD in network science, holds a special spot in my heart when it comes to geospatial data. So today we will learn about the City-to-Graph package, which has been gaining popularity over the past few weeks or even few months. Essentially, it's a very neatly designed package which connects various layers of geospatial data once we feed in the right inputs, and then allows us to analyze cities as graphs in a very handy way. So let's see how it works in Python. As usual, I will add the link here as well, and the command which you can run to install it even directly from your notebook. Today's tutorial, we will learn how to quantify cities and analyze them from the 15-minute city perspective. The 15-minute city perspective quantifies the quality of life in urban areas based on the reachability or availability of necessary public services and necessary locations, so essentially POIs, such as education, healthcare, recreation, and shopping. And it says that if all of these services are reachable in 15 minutes by either walk or bike from home, then it's a livable spot. So to move on, let's import the necessary things and also confirm the City-to-Graph version I have here. Then I will write a short piece of code to test the package. And we will test it on the example of Budapest, which I'm sure is not very surprising at this point. So we will get Budapest. We can plot it just to make sure we know how it looks like. And then we will get the POI data from OSM using OX as usual. Here I will focus on sport facilities, so various gyms and sports centers. You might also have seen this in the first day of the 2025 map challenge from me and in my tutorial. So here we have the points. We make sure that all of the geometries corresponding to POIs are actually points, and then just clean up the data frame. Once we have the POIs, let's have a quick look at the data frame, and we can also plot them just to see how they look like. And yep, they are indeed all around the city of Budapest. Then we will start using and exploring the City-to-Graph package. First, let's see what are the things here. So there are loads of things. So from here, we will use a few graph functions. For instance, the Waxman or Waxman graph. So what these functions do, essentially they take the POIs as an input, and using various underlying logics and networks and network concepts, it will reconstruct the graph of these POIs. So the most simple one, and now I will first define the radius to be, let's say, 2.5 kilometers, which is fairly large, or maybe even smaller. Let's do just 1,000 meters for now. So the first one is going to be the fixed radius proximity graph. So this graph will connect all the pubs that lie within a fixed Euclidean distance of 1000 meters from each other. So it's a very simple geometric thresholding thing or threshold-based network which captures direct proximity. So this could be an easy way to capture clusters and studying various local densities, but it's not based on actual walkable distance, so this might actually be better used in, for example, agricultural use cases where we don't really have roads that we would care about. Also, to see how this works, maybe even before that, let me define a function which will plot a single connectivity graph like the one we will query here. So I just copied the interface from my notes, but here this graph will create a canvas where we will plot the admin input like Budapest or other cities as we will do later on. The edges which we will get from the city to graph functions. And for example, let's add the base map and some simple fine-tuning commands, which we usually do, setting or switching the axis off, setting the title and the title layout. So then, once we go back to the fixed radius graph, let's see how we can visualize it with this function. So, not easily, if we don't have context till I import it, but I will go back here and import it right away as CTX. So let's see. Yep, so this is the simple connectivity graph of Budapest where with blue now we see clusters of nearby sporting locations or sport facilities being highlighted. Here there is a lot, but it seems that 1000 meters is not that big of a deal. So let's go back to my default 25,000. And yeah, this already looks pretty cool. So this is a nice connectivity graph, even though this doesn't consider that we have to use roads to move around the city. It already hints some nice basic structure. So let's see how we can make this even better. For example, by using this so-called Waxman graph. Same thing, city to graph, calling the function. It takes the POIs. Here we can specify the distance, the radius, and a specific parameter. So while in the previous case, every nearby location was connected for sure if they were within reach, here we only connect nodes or points with a certain probability. So this Waxman thing connects nearby places based on radius according to a given likelihood, which is defined by an exponential distribution, which takes one parameter, this beta value. Also, here now we are using a Manhattan distance metric, which simulates pedestrian movement well in grid-structured cities like most of the large American cities. So it's actually still not the best suitable tool for Budapest, but as you will see, it also gives reasonable results and looks nice and tells us how this methodology works. So here, this is a very different network based on how it looks. This looks completely organic and kind of discards any regard to spatial relations like road network structure and how buildings and other spatial features like the river here in the center are located. While here, we also discard most of those structures and use this artificial grid instead of the actual road network. But we are getting there and we are still having fun with these beautiful, colorful networks. So the next one is going to be still a Waxman tutorial. So now we are going for the Waxman, but with Euclidean distance metrics. It should generate a smoother image, a smoother network with more isotropic connection patterns. So we won't be aligned to these two coordinate axes. So it should be a bit more organic and look a bit better like a city, an actual city. Let's see how this will look like. Yep. So this is sort of a mix of this very grid-like structure, very artificial, and this totally random graph looking thing. So it looks nice, interesting. I will print it and hang it on the wall as an art piece, but it's still not the best thing for urban analytics. But don't worry, we are getting there. Oh yeah, I just realized that this shouldn't be called plot pub, but that's just a tiny side note. So now we are moving on to using the real street network, for which I'm going to use this quite convoluted command, but let's see what it is. So I believe that we defined the city name to be Budapest. Yes, we have it here, Budapest. So then we will use the graph from place command from OX and then query the drivable road network. We should, for proper 15-minute city analysis, download the walk network, but I want to keep things smooth and simple and computations easier. So I will download the drivable network and then turn that network into a GeoPandas data frame which will contain all the road segments as line strings. Then we will go back to the city to graph library, and now we will use the network distance metric in the Waxman algorithm, which means that now we are going to model the possible mobility pathways between locations, between sport facilities, between POIs, in a much more realistic way, because here now we will only allow connections to be made that are present in the road network. This will also mean that this computation will probably take a lot longer than the previous ones. And while it finishes, I will look for the quick visualization command and code for this network. So again, we call the function from city to graph, we define the POI, we define the distance metric and the rest. And then as an additional parameter, we input the road network as a GeoPandas data frame. Okay, we got a warning, but hopefully the computation will go through. And here we are, and now we have a beautiful, nicely weighted road network of Budapest. So this is the connectivity network of all the sport facilities. So this shows that which parts of the network, which parts of the city are well connected within this distance framework or within this distance limit range to each other and to the sport facilities. So now let's move on towards the 15-minute city concept and see how we can reach essential services. Just to make sure we have everything in one place, I will add these initiation or initial code parts here once again. But I'm not running the cell because they are loaded in the memory. Then I define the list of POIs. So for now, I will visualize 4 categories of POIs: active life, so we can do sports; daily needs like shopping; social life; and healthcare. But you can extend or change this list or focus any specific category if your use case requires you to do so. And then let's create the Wax graphs for every single category using the network distance, the road segments we just queried, and a smaller radius, 1000 meter, which is 1 kilometer, which if we are walking at an average pace should be around 10, 12, sometimes even 15 minutes. So now we are decreasing the radius. So once this loop is finished, we should have 4 lists of edges for each of the main POI categories. So now let's visualize them. First, by assigning a color. Here I'm picking bright neonish colors for each layer. Then let's define the canvas size. Oops, that was a bit of a spoiler. Let's tune it down to 7 inches or 6 inches. And first plot the boundaries. And also for housekeeping, I will add the usual stuff. Also, let's add the base map. Here I'm gonna do core2db dark matter, so it's gonna be almost black without any labels. And let's also fine-tune the title. So we will define it as Waxman network distance, specify the font size, the position and the color. And now after all of these things, let's finally visualize the edges. So we will iterate over the 4 different layers. And within each layer, we will iterate over each geometry, extract the coordinates, and then plot them. As simple as that. Also, just to make sure we know where the actual locations are, which are connected within each graph, we can also iterate over the layer of POIs and plot the POIs as well. And once this code finishes, here we will have a nice detailed map of Budapest. Here the central is very busy, so maybe we should tune up the figure size after all. It won't fit the full screen, but we will have a better look on how it looks like. And while the figure renders, let's get prepared for the last part of this tutorial, where we are going to do similar visualizations across multiple categories for multiple cities. For that, I will define a new function which we are going to call plot city connectivity. Yep, here it is. So that's a detailed map of Budapest covering 4 different categories of the daily life. Active life, sports and gym marked by blue, which is, as it seems, quite marginal compared to social life, cafes and restaurants marked in pink, while health services like doctor's offices or pharmacies in green are also quite small. And in yellow you will see the daily needs, which are probably the second most visible here. So now let's get back to defining this function, plot city connectivity, which will take a city, the admin polygons of the city, but we could also move it inside and write the OX part within. But for now, let's use it as I have it prepared. The POI layers, the graphs, and the radius. And here we will essentially just bring together all the pieces of code that we had before. So we define the canvas, we plot the city boundaries, we draw the network edges. Here you will see a little difference. So here I have a wider and more opaque version, which kind of adds a mild glow to the edge lines. And there is a thinner but stronger line as well. So this way we will have the core of the road network in a stronger design with a soft glow around it. We also add the base map and the axis. And here I will have a longer part to define the boundaries. So as I was testing this code, it turned out that for different cities, different boundaries would make sense. For example, for certain categories in different cities or certain cities, the majority of the POIs were in the center, so if we would just automatically plot it using this piece of code, it wouldn't look as great as it did for Budapest. So to get rid of those awkward situations, I will define the X and Y limits of the plot based on the bounds of the edges. So for this function, let's call AutoZoom. First, we will get all the bounding boxes for all the edge lists. And then we will pick the extremes, because, in some categories there may be POIs on the outer parts, while in other categories POIs might not spread that much out of the city. So the buffer we are gonna add is gonna be the 5% of the total span of the data across the X and Y axis. So this tells us the exact spread from left to right and from top to bottom we have on the map, and then this way we are adding some padding with 5% coverage in both directions, and then all we have to do is to set the X and Y limits accordingly. We are not done yet, but let's see how this function works. And as a test, I'm going to run it on one city, but for this part we will create visuals for 4 cities: Zurich, Vienna, Budapest, and London. Again, we will make sure that we also have the colors, and we will work with a 1 kilometer radius once again. And to make sure everything is in one place, here I will also add the POI categories once again. So if we have all of this here, then let's iterate over the cities, but for now only focus on Zurich. It's also the smallest, so the function runs the quickest for it. Let's add some printing commands which prints what's happening here. We will add the part which downloads the city graph, then the part which downloads the POIs, then the part which builds the graphs. It's really just a nicely structured recap of all the things from before, and then the plotting command. So now we will have to wait a few seconds until we get all the data and we visualize it, but here you can already see that Zurich is a lot smaller than the other cities, and it's gonna be there very soon. Yep, the usual bug. Let me correct it very quickly. CTX. And by now everything should be loaded, so all the data is in the Wax Graphs dictionary. So now I will do something that I believe that no engineer would approve, but I will copy this line and bring it up here just for the development phase and run it once again. So now this should produce the figure of Zurich right here. And here we are. So now you see that here are the networks of Zurich, 4 layers, and also the boundaries. So let's see what happens if we comment out this part. So you just see why I was working on these through so many lines. Yep, so now we have a bit wider spread, but Zurich is fairly small and compact, so it doesn't make a huge difference, but still this looks better in my opinion. Okay, so we have it like this. So the next thing I want to do is to get rid of this here. We are grateful for OpenStreetMap and Carto for the data and the base map, but we don't want to be reminded every single time we look at the map. So the way we will get rid of everything outside of the city boundaries, including this important but quite ugly title, is to create a mask which is the inverse of the city boundaries. So for that, first we will need to create a bounding box polygon, which will cover the same area as the visually visible part. Then we will have to take the shape of the city from the admin polygon and take their difference, which is going to be the mask. Then all we have to do is to plot the mask in all black and making sure that it's below the network lines, so it's not covering any useful info by any chance, but above the base map. And if we do that, then we get rid of most of these things here. And now there is just a few little things left. So on the one hand, the regular housekeeping, adding the title and adjusting the layout, and then adding the legend box. So the legend box is going to be quite complex. So let's put it together first. So we will have to iterate over the layers, and this is going to be a Python list comprehension, which is going to be called legends. So we iterate over the layers, And for each layer, we will create a line that's going to be the legend item. And then we specify its location, width, and the title. And then, let's see if the code is correct. And then we will have to add, okay, now it's defined, but it's not visible yet. And here we still have some leftover from the OSM logo, but we will get rid of that very soon as well. And for that, let me just add this really long legend instance. It's long, but nothing new, so we will have to use the handles we defined here. We will set the exact position. We will have the frame on, and it's going to be totally black. So that way we will black out anything that would be visible here. And then the usual formatting stuff. And if we run it, then we will have a nice text box here as well. So now we have everything in place. Let's delete it here. And now if we run this piece of code, then it should create a complete visualization for Zurich and then for all the other cities. Here I have to admit that these computations, especially for London, take quite a few hours. So I'm not going to run them now, but I will show you how the results look like. Make sure that this part works, so we don't leave anything here like half-baked. And then we will list all the images that I exported before that were produced with this piece of code. Yep, here it is. So see, it runs perfectly well. So now here we have all of these images. And with this function, with this image function, we can display existing images in a Python notebook very quickly. So now this is the full resolution. You can see that it's quite high definition, but we don't see too much here. So let's see how London looks like. It's not England, it's UK. And yep, so this is London, so it looks really cool, right? Here you can also see that the yellow one, so the daily needs, dominates the city and it's covering the majority. While there are very clear spots where green health services are available nicely, and there are parts which are lacking. Of course, this is only one layer of information. And here we are using the driving and not the walking road network, just to make it a bit more simple. But still, if we would compare this visualization and this landscape with a bunch of other London data, for example, socioeconomic conditions, house prices, mean salaries, and of course, population or the location of green area, we would probably see a correlation and we could figure out whether there is any link between, for example, a place being fancy and expensive and having good access to healthcare or sporting opportunities. But that question and that project is for later, because this topic today was how we visualize OpenStreetMap data. And as OSM goes, I usually enjoy and love working with road networks. I think that they are really pretty. And thanks to the City2Graph package, I think that now we have another really great tool to emphasize this point and show the world how beautiful city networks can be. So thanks for following, and let me know how your city networks look like. And if you would happen to visualize any cities, especially your hometown, then make sure to reach out so that I can also have a look and also share it. So thank you and see you next time. Bye.